My name is Sebastian and I'm a second-year PhD student at CISPA and going to tell you a tale of two headers, which is a formal analysis of inconsistent click-checking protection on the web. This is joint work with Stefano and Alvise from University of Venice and my supervisor Michael and my advisor Ben from CISPA. First, let's start with a short refresh about click-checking attacks. Here you can see a nice cat picture as it is common throughout the web. Everyone loves them, right? So everyone wants to see more of them and click on the yes button that you see on the right side. However, clicking on buttons might be dangerous due to click-checking attacks, where an attacker lures the victim into clicking on, for example, an instant buy button, which is in an opaque iframe that overlays the yes button. To defend users against that problem, Microsoft started the Xframe options header in 2008. However, in the meanwhile, the header is deprecated because it has several problems. It is only partially supported in browsers. Those that support it have inconsistently implemented the header, which leads to security problems like double framing attacks. Also, because you can only whitelist a single origin in Xframe options, it is not usable for sites that wants to be frameable by multiple of their partner domains. In order to fix these issues, CISP introduced the FrameCheck directive in level 2. With this new directive, framing control can be done in a well-defined, secure and usable way. However, the problem now is that web developers may choose to use any of these two mechanisms or a combination of them to protect their web application. Given this complexity and the diverse levels of support for framing control, this potentially gives rise for inconsistencies. Those inconsistencies were the main motivation for this work. We tried to figure out if we can formally describe the inconsistency between Xframe options and CISP framing sisters. Also, we want to know how inconsistent framing control is implemented in different browsers and how it is deployed on real-world websites. Furthermore, we ask us if we can automatically fix inconsistencies between Xframe options and CISP framing sisters. Now you might think, why the hell is this a problem? Either a browser supports Xframe options or framing sisters. However, not only the support itself might be inconsistent. Also the behavior if multiple Xframe options or CISP headers are present in a response differs. Also different is the way how headers are passed and also against which frame the value in the framing control header is checked. As a first step, we started to distinguish between modern browsers in blue, so those that support frame ancestors, and legacy browsers in red, which do not support the CISP directive. Now, with this semantics of browser behavior, we started to create a formal framework. But first of all, we need to have a relation that allows us to order the directive values of our headers. Luckily, Calzavara et al. Presented Core CISP in USENIX 2017. They have defined a relation that states that v1 is contained in the set of origins represented by v2. Now we can use this relation to define the consistency of framing policies. A policy of a web page W is consistent if all browsers are equally protected. The double square brackets that you see in the formal definition here denotes the semantics of the browser B for the framing control deployed by website W. To give a more concrete example here, a website that only deploys Xframe options allow from example.com to control the framing has inconsistent framing control because it restricts framing in Microsoft Edge, but it leaves Chrome users completely unprotected. To improve the protection, the website might additionally deploy CISP framing sisters example.com. Thus, the revised framing control policy is consistent for Edge and Chrome because CISP takes precedence over XFO. Hence, the users of these two browsers are equally protected. Another important definition is about whether a policy is security or compatibility oriented. A framing policy is compatibility oriented if it restricts modern browsers less or equal to legacy browsers. However, a policy is security oriented if it restricts legacy browsers less or equal to modern browsers. But let's have a look at some examples here. If a web application hosted at example.com deploys Xframe options allow from advertisement.com, the framing policy of example.com is not compatibility oriented, since two modern browsers like Chrome and Edge give different interpretation to the policy. Edge supports the allow from mode, while Chrome lacks support for it. In case of example.com deploying frame ancestors star.example.com as well as XFO same origin, the revised policy is inconsistent because legacy browsers that do not support CISP's frame ancestors cannot be framed by, for example, mail.example.com. However, because users of legacy browsers are inconsistent but still more protected against framing-based attacks than the modern clients are, the policy is security-oriented. As already mentioned in the beginning, we also want to have a look on how inconsistent framing control is deployed in the wild. In order to get numbers about the inconsistencies of framing control in real-world web applications, we started an experiment involving the Tranco top 10K websites. For these websites, we collected up to 500 URLs per site and gathered the framing control headers from those URLs. We then used our definitions from before in our FrameCheck framework to classify those headers into inconsistent, security-oriented, and compatibility-oriented policies. The source code of this analysis is available at the CISPA GitHub account, but for now let's have a look at those numbers. Our crawler visited a total of approximately 1 million URLs, out of which a little over a third had some form of framing control. We then aggregated the different policies on origin basis. For example, if all pages under a given origin have the same Xframe options header, we only count that once. This leads to 70,000 policies in total. The vast majority of sites makes use of Xframe options to protect the application, and only around 2% do so inconsistently, which can be addressed to the fact that most browsers support Xframe options and that most of those policies are same origin or deny. Considering sites that only use CSP, albeit it's obvious lacking support for some browsers, which means they are all inconsistent, not all are. Some CSPs just allow framing from any origin, which is consistent with not understanding CSP at all. Finally, there were also pages with both XFO and CSP. Here more than half of them delivered inconsistent protection. Overall, the 805 inconsistencies amount to 45% of all observed inconsistencies, which confirms the intuition that having two different mechanisms for the same purpose is potentially dangerous. Based on the numbers that we have just seen and based on the policies that we analyzed, we then created recommendations, countermeasures, and a piece of software in order to fix the issue. First of all, the best way for a developer to defend a web application against framing-based attacks is to use both Xframe options and CSP to secure modern and legacy browsers. Also, because of the inconsistent behavior in how multiple headers are evaluated, we recommend to only deploy one single Xframe options headers for each request. In addition to that, we encourage operators to not use comma-separated headers, because the parsing behavior of browsers differs in this case. We have also defined recommendations for browser vendors, but for time reason and because the probability that they would adhere to those are relatively small, I would refer you to the paper for those. Another thing that we have done to ease the deployment of a sane framing control for website operator is we created a server-side proxy. This proxy acts as man in the middle between the client and the server. It first inspects the incoming request to map the request to the response and to collect information such as the referrer header. Afterwards, the traffic is just as usual processed by the web application, and as soon as the web application returns a response, the proxy intercepts that response in order to make the framing control consistent. For example, it converts CISP's frame ancestors into the corresponding X-frame options header and vice versa, such that all clients are protected. If you want to know implementation details, I would again refer you to either read the corresponding section in the paper or take a look at the source code in the CISPA GitHub repository. Okay, now, what have we seen in the last few minutes? Well, the way of how browsers handle framing control headers differs significantly. We use our formal definitions from our FrameCheck framework to find out how inconsistent framing control is used in the wild. And finally, we presented recommendations and countermeasures as well as our framing control proxy in order to fix the issue. So, thanks for your attention and feel free to ask questions.